Hi ladies and gents. In Unit N, we looked at how to calculate probabilities for the normal distribution by hand using tables. I'm going to show you how to use Excel functions to do the same thing. So I want to take a look at some problems here from Unit N. And the first one comes from page N10. And let me actually just take you back over there. So this is what we did in class by hand. And it says, consider the marks for 50 students. The distribution is normal with a mean of 60 and a standard deviation of 12. I'm going to show you how to use Excel functions to do some of these problems. We're going to look at D first, and then we'll work backwards up to C and B. And that basically covers every kind of problem that we need to look at in these couple of pages here. So let's take a look at D. And D was just a simple probability here. What's the probability that X is less than 50? Or what percentage of the class have marks less than 50? And so when we did this by hand, what we did was we calculated over here a Z value, and that was based on this picture right here. So we're looking at 50 down with a mean of 60 and standard deviation of 12. And so we standardized this and we came up with a Z value, and then we went to a table and we found out that the probability associated with actually this area in here was 29, about 30%, and so what was left over in the shaded part here was about 20%. So that was the answer there that we did. Now let me show you how easy it is to do that with a normal distribution function. And I'm going to be using a function here called the NORM.DIST function. Let me show you where you find this, as well as where you find all the normal functions. So if you go up into formulas here, and I'm using a Mac, but it's exactly the same setup with a PC. And so we're going to go to Formulas, More Functions, Statistical. And under statistical, you'll see that there's a whole bunch of really good stuff here. And in particular, down here, we've got some norm functions. So we're going to take a look at the NORM.DIST function and the NORM.INV function. And we'll briefly talk about the NORM.DIST and the NORM.INV function. But here's the one that we're going to start with here. So that's the NORM.DIST function. And what I should do actually is just get in the right spot first. It's always important that you make sure that you've selected the right cell. So I'm going to push escape there. And I'm going to actually put the formula right here. So I'm looking at what's the probability that X is less than 50. And so I'm going to go back there and find the NORM.DIST function. And over on the right hand side, you'll see the formula builder. On a PC, that will just pop up as a little pop-up menu or a pop-up input box there in the middle of the screen. Now, what you'll see here is that there's 4 things that you need to put in, and I've got them in red up here in cell B5. So right in here. So the first one that we put in here is our X value, and our X value then is the 50. So over on the right hand side, I'm going to type 50. And then I'm going to drop down to the next box here, and I'm going to put in the mean, which is 60. And then the standard deviation is 12. And then the last one here is cumulative, and it's true or false. And for a normal distribution, we'll always use true. So the only time that we're using false is when we're using the binom.dist function in this course. But we're going to put in here true. And so that gives us then 20%, which was the answer that we got by, if you go back over here to when we did this by hand, we got 0.2033. It's a little different because this, when we calculated the Z value, we took it to 2 decimal places. And it's actually 0.83333, and so it's a little bit different, but certainly to 2 decimal places, it's exactly the same, so it's 20%. So I'm just going to actually copy that there I'm just going to move that over, and I'm going to put a little apostrophe in front of it so you can see the actual function then that I use there. All right, so that's how we use the NORM.DIST function. The important thing to note is that that is giving you the area from some point all the way down. So if we were looking at, say, the probability that x is less than 90 or something like that, it would give you the probability all the way down to the bottom, not just to the middle, which is what the table gives you, but all the way down. All right, let me show you the next one here. This is the probability that x is between 70 and 90, and all we need to do in this case then is to use two NORM.DIST functions in the same formula. Now, I can go up here to formulas, more functions, choose NORM.DIST, but once you've used it a couple of times, you can just simply start typing it in. So notice what cell I'm in. I want the answer to go right in here. And so then I'm going to put in equals NORM.DIST, left bracket. And it might be a little hard for you to see down there, but it's asking me for the x value. So the x value I'm going to put in there is actually the bigger one, which is 90. So the one which is further to the right, and then comma to separate the arguments, 60, which is our mean, comma, 12, which is our standard deviation, and then true, minus NORM.DIST 70, comma, whoops, comma, 60, comma, 12, comma, true. So remember, we always use true as the last argument, and it's the x, the mu, and the sigma. The one thing to note here is that, of course, it's always more efficient to put those numbers into boxes, into cells. So I would have the mean of 60 in some box, and then I would have the standard deviation of 12 in some box or some cell, and then I could reference those, and that's better. But when you're doing this on an assignment, it's a lot easier for me to mark if you show me the actual constants. So it's not as efficient, but it's a lot easier to mark. Anyways, there's the answer that we get, which is 0.1961. When we did this up here, so this is the purple stuff, we calculated Z values for the 90 and the 70, so we converted them into 2.5 and 0.83. We looked them up on the table, and then we found the areas, and then remember that gives you the area down to the middle, and the NORM.DIST function by itself would actually be 50% more of that, so it would be 0.9938. I might just take you back there and just show you that part. That would be from 90 down. But then we subtract off this probability here, and that gives us 0.197, which is what we had here, 196. Again, it's just a little different. I just want to, well, let me copy that first, and then just go and put an apostrophe there, like that. I'll make this just a little smaller so you can see the whole thing. There we go. If I had just done the last one, the first one here, which would be from 90 down. Let me just show you what I end up with then. See, there's the 0.9938, which is pretty close to the point. Well, there it is, 0.9938 is when you look up 2.5 on a normal table. And this gives you down to the middle, so then you'd add another 50%. So the NORM.DIST goes all the way down, not just to the middle. Right, so that's what we've got there. I'm just going to copy that one back across here, because the answer actually was 19%, or 20%, and so there we go. All right. I'm going to just increase this a little bit more. Let's take a look now at the probability that x is greater than 90. Whenever you're going from some point up, you always start with 1 minus. and then it's 1 minus that point down. So it would be from 90 down. So it's going to be 1 minus NORM.DIST 90, 60, 12 true. And that gives us then about 0.0061. And is that what we had up here in B? Yeah, 0.0062. So about it, almost exactly the same there. Okay? And let me just give you that function over here so you can go back and take a look at it. So that's how you use the NORM.DIST function for calculating some simple probabilities. Now, down here I've got something just really as an aside, but it will come in useful when we get into the next unit, which is in Unit E on estimations and when we're building confidence intervals. And this is a function called the NORM.S.DIST. And I want you to think of NORM.S as being Z. So it's the Z distribution, the standardized normal distribution. Now I want to go back here. I'm actually looking at 4D, which was this one right here. So the probability that X is less than 50. And so that was the one in red here. When we did this by hand, we standardized the 50. So 50 minus 60 over 12, we got minus 0.83. And just to show you then that if you stick that Z value in, all you actually need here then is the NORM.S function, DIST function, and you put in the Z value and true. So I want to build that for you. Is equal to NORM.S.DIST, and all it asks you for is the Z value. So this was minus 0.83, and then you still need to put in the true, like that. And we should get the same probability as up here. And again, it's pretty close. Remember that this was actually minus 0.83333. That's why it's just a little bit different from up here that we have there. But it's the same kind of thing. Now, the thing to note here is that you should not usually have to use the NORM.S.DIST function. You will when you're going to be building confidence intervals, but in this particular example, when you're given the X value and you're given the mu and the sigma, just use the NORM.DIST function. Don't go and calculate a Z value and then stick it in, because you're just doing an unnecessary step there. Let the computer do that for you. But I just wanted to show you that you'll get the same answer, and it does introduce you to the NORM.S.DIST function. All right, let's continue on down here. I suppose what I should have done was actually just pulled those guys down here. There we go. Now they're in the right place. Now the above was when we are given an X value, a mu, and a sigma, and we wanted to find a probability. So that's what the NORM.DIST function looks at. What if we are given the mean and the standard deviation, so mu and sigma, and we're given a probability, and we need to find the appropriate X value? That's what we were looking at on page N11. So finding an X, a mu, or a sigma when the probability is given. So here's the problem that we had in number 5. This is on page N11. Remember N11 is, anyways, it's N11 on number 5 here. Consider the marks for 50 students. So we have a mean of 60, a standard deviation of 12. What mark would you need so that only 10% of marks are higher than yours? And so what we did here then was we said, okay, we're given the probability. You can't really do a standardization here because we don't know what the Z value is and we don't know what the X value is. However, we can use this probability to, excuse me, to find an equivalent Z value. So what we did was we went over here and we said, okay, let's find a Z value that has 10% above, and that means that we have 40% from here down to the middle. And then we went to a table and we looked that up. We looked up the 40% in the middle of the table. We read out to the sides of the table, and we found that that was 1.28 right there. And then we just went and plugged that into a formula here. We're going to be using something called the NORM.INV function. And that's where you're given the probability and a mu and a sigma, and it returns as an answer the x value. The important thing I want you to note, though, is that when we did this by hand, we said there's 10% up from z, or from the original x, and so that's 40% down to the middle. It actually calculates the probability all the way down to the bottom here. So it wouldn't be 40%, it would be 90%. 10% up, 90% down. Let's take a look at what we've got over here. So this is what we've got. Again, x is normal, mean of 60, standard deviation of 12. We want to find an x value so that 10% of the distribution, or the marks in this case, are above that x value. We need to think of it in terms of, well, what percentage would be from that point down? And that would be the complement of 10%, which is 90%. 90% of the marks are below the x value. This is the function that we're going to use. It's called the NORM.INV function. And you see that the first argument there is the probability. So that's expressed as a decimal value, and that's the 0.9. From that point down. It's always from some point down. Then we put in the mu and we put in the sigma. It doesn't ask for a true or a false in this particular case. Let's go and build that now. So I'm going to go right here. And I'm going to go for more functions. Statistical. And down here, so we've looked at the NORM.DIST, the NORM.SDIST. We're going to look now at the NORM.INV function, and then we'll briefly take a look at the NORM.SINV function. So those are the four norm functions. So let's look at the NORM.INV function. And so it asks for the probability, and that's where you type in here the 0.9. The mean, so that's 90% from that point down. The mean is 60. The standard deviation is 12. And that gives us 75.3786. And I'm just going to copy that and move that over here. Let's see, is that close to what we got when we did this by hand? So 75.38 or so, and we got 75.36. So again, the difference is only in terms of this z value, which is rounded to 2 decimal places. So we're really close there. One thing to note here is that we are going from some point up, and so you do the 1 minus part, but it's actually right in here. It's the probability itself. Whereas when you're doing it with the NORM.DIST function, you do it on the outside here. 1 minus the NORM.DIST from 90 down, and that would give you the probability of x being greater than 90. So you're still doing the 1 minus, but the 1 minus actually is done right inside the first argument, the 0.90 there. All right. So that's what we've got. There's the answer there. And actually, I'm in the wrong spot there. Let me pull that up. It should be right there. Because I do want to show you then the NORM.SINV just as an aside here. And this is actually, if we were, what would be the Z value associated with 90% down. And so let's just take a look at that. That would be a NORM.S.INV. And all it asks you for is a probability. That's all it is. So you just put in 0.90. And remember, it's always from some point down. So if we want the upper 10%, that means the lower 90%. And it gives us an answer 1.28. Now, it's a positive 1.28 because it's on the upper tail. But that's what we end up with. Let me just put in a 90 there just so it's a little easier to read. That 1.28 is this guy that we got right here when we looked up the 40% in the middle of the table. Remember, we're not going all the way down 90% on the table, we're going down just to the middle. So we look up the 40% and we get 1.28. Do you want me to take you there? Let's just really quickly go there. So I'm going to go to, yeah. So when we did this by hand, what we did was we said, here's 0.3997. That's the closest that we have to 40%. Remember, we've got 10% here, and we've got 40% here to the middle. And so we read out and we get 1.28. So that's how we did that. Oops, let's go back just a little bit there. All right. So that's where we got the 1.28 from. And again, we just can use a NORM.S inverse function. In this particular example, you don't need to use a NORM.S inverse function. You can just go straight right here because you're given the probability, 10% up means 90% down. You're given the mu of 60, you're given the standard deviation of 12. So you would just simply use the NORM.inverse function. All right, so there are the 4 norm functions. I want to take you through a couple more problems though. Now, the NORM.DIST function is used when you have an x value, a mu, and a sigma given, and you're looking for a probability as an answer. That was the first thing that we looked at here in this lesson. Then we said, well, what if you're looking for the x value, but we're given instead a probability, but we have the mean, the standard deviation, and probability, and we're looking for an x value? Well, that's where we use the norm inverse function. But what happens if one of the parameters, either mu or sigma, is what we're looking for? This is what we had in this problem here. This is on page N12, number 6. And this is the bottling company problem. So let's take a look at how this works here then. Bottling company wants to set its filling equipment so that on the average only 5 bottles in 200, that's 2.5%, will contain less than a minimum net fill of 400 mils. Assume fills are normally distributed with a standard deviation of 5.1. What is the mean? And so that's what I've got right here then. I've drawn a little picture here. Here's the 400 associated with 2.5%. And we've got a standard deviation here of 5.1. What is the mean? And what we did was we couldn't go straight into a standardization formula because we don't know what the mean is. And so we went to a Z distribution and we said, well, what is that Z value that has 2.5% of the distribution below it? And it turned out to be minus 1.96. And then we plugged that into the table here, or into the formula, and we ended up with 410 as an answer. So that's how we did that by hand. Let me show you how to do that with Excel. So I'm going to come back here. Here's our problem. And so we have an unknown mu and a standard deviation of 5.1. We are given this probability. The probability that x is less than 400 is equal to 0.025. What is the mean? What is mu? So what I did was I set up a little table here that looks like this. So here's the x value. Here's the mean, which is what we're looking for, and I'll explain this in a sec. I'm just going to put in some number 1. You can put in 10, you can put in whatever you want. Sigma is equal to 5.1, and this orange cell here is where we put in a NORM.DIST function. So I've actually typed it out over here. This is the NORM.DIST function. And what it's doing here is it's using the arguments, the x, the mu, and the sigma. So it's using cell referencing for those. And it's important that you do this with this thing called the goal seek. It's true that you could actually type in constants for the 400 and the 5.1, but you'd need to put in D37, which is my cell reference of where the mean is, because that's the one that you're looking for. So anyways, that's how we do that, is we set these up as cell references using a NORM.DIST function. Now, right now, I've got just a value of 1 in there. And I could leave that blank, or I could put in my best guess, which is going to probably be close to 400. You know, I could put in 450 or something like that. But it's important that you put in a value. It's not actually as important with the mean for mu, because if you leave it blank, it has a numerical value of 0. But it doesn't work if you're looking for a sigma, because if you think of your standardization formula, z is equal to x minus mu over sigma. If you had an initial value of 0, which is what a blank cell is, then you'd end up with an error message, right? You can't divide by 0. So just put in a value. I always start with 1. Whether I'm looking for a mean or whether I'm looking for a standard deviation, I would put in 1. All right, now this is where it gets really cool. You're going to make sure that your cell has selected the cell that has the NORM.DIST function. So in this case, it's D39. That's the one that has the NORM.DIST function, and the NORM.DIST function needs to have cell references for the different arguments. We're going to go up here to the data ribbon. And this is the same on a PC version of Excel as well. Data, what if analysis, goal seek. All right, so data, what if analysis, goal seek. And that brings up a little dialog box that looks like this. Now, the set cell needs to be the cell reference of where you've got your formula. So that's why I started in D39. So D39 has the NORM.DIST function. The to value is the answer that we were given, which is 0.025. That's this guy right here. Remember that a NORM.DIST function always gives you the area from some point down. So if we were saying 10% of the values are above something, we would have to put in 90% there as an answer. But this one here says that 5 out of 200, or 2.5%, are less than the minimum 400. So we put in the probability. Remember, a NORM.DIST function gives as an answer a probability. And so we want the answer of the NORM.DIST function to be 0.025. So that's the to value, and you just type that in as a constant. Here's the important part here. By changing cell, and this is where we click to select cell D37, because that's where we have our mean. And what it's going to do is it's going to try out, using an iterative process, different values of mu until it ends up as an answer for the NORM.DIST function of 0.025. Let's try it. So I'm going to click on the OK, and this is pretty cool because it goes through an iterative process here, trying out a whole bunch of different things here. And there it is. 410 is the answer, which is what we got by hand. So then what you do is you just simply press OK, and that is the mu that we got when we did this by hand over here. All right, there's one more thing that I want to show you here, and that is doing a normal approximation for the binomial. So I'm going to take a look actually at the problem on page N16, number 11. Let's go over there and take a look at that. So we're taking a look at normal approximation of the binomial probabilities, and specifically then page N16, number 11, right here. So Mr. Adams, who sells compact cars, believes that the probability of selling a car for any given customer is 0.3, 30%. So that's our P for a binomial problem. If in a given week he contacts 100 customers, that's our N, what is the probability that at least 35 will buy? So what we did was we went through here and we said, okay, this is what we're given. The parameters, N is equal to 100, P is equal to 0.3. We need to do this check, right? Is N times P at least 5? Is N times 1 minus P at least 5? Check, check. And then we need to do this correction for continuity. And in our particular case, then, this problem said at least 35. Where is that? Yeah, at least 35 here. So that means 35 or more. So that's what we have right here. So you always want to make sure that you've got the equality. If it said greater than 35, then we would actually be starting at 36. But this said at least 35, so it includes 35, so it's greater than or equal to 35. Then we do the correction for continuity. And if we're going from some point up, what we do is we drop down a half, 0.5. So if we're going from 35 up, then the equivalent in a normal distribution would be from 34.5 up. If it was 35 down, it would be 35.5 down. And then we went and did this by hand. What we did was we used this standardization formula here, recognizing that, remember, for a binomial distribution, mu is equal to n times p, and sigma is equal to the square root of n times p times 1 minus p. And we end up with an answer here of about 16% down here as an answer. So let's take a look at how we would do that. I'm actually going to do this using both the binomial distribution and the normal distribution to show you that they're really close. So this is what I've got down here. N is equal to, x is binomial, n is equal to 100, p is equal to 0.3. Show me your check. So this is 0.3 times 100. So 100 times 0.3 is n times p, right? And then the 70 here is 100 times 1 minus 0.3. So these are both greater than 5, so check, check, we're good to go. Here's our mean, here's our sigma. So the equivalent then, remember, mu is equal to the mean of the mean of a binomial distribution is equal to n times p. So that's a 30. That's the same thing up here. So that's 100 times 0.3. And the standard deviation is equal to the square root of 100 times 0.3 times 1 minus 0.3. So that's what we've got there. Okay. Let's go and build this. If we were to do this as a binomial problem, this is how we would do it. We're going from some point up, so we have to start with a 1 minus binom.dist, and then it asks for the x value, the number of successes, so the x value. Now remember, if we're looking at 35 up, what is left over? What's left over is 34 down. So we need to put in 1 minus 34 down to leave us with 35 up. Remember, this is a discrete distribution. So we are jumping 34, 35. You can't have 34.5 successes. Comma. Our number of trials, which is 100. That's our n. Our probability of success, which is 0.3. And then true. Because whenever we're dealing with an inequality, we put in a true. Now, what does that give us for an answer? 0.163. Let me just show you that function again, right there. Let's do this now as a normal distribution function. 1 minus, because we're going from some point, we're going to 34.5 up. So we need to go 1 minus norm.dist 34.5 down. Remember, this is a continuous distribution. So the complement of 34.5 up is just 34.5 down. So 1 minus norm.dist 34.5 comma, and then the mean, which is 30, and then the standard deviation, which is 4.583. I usually take these to about 3 decimal places, and true. And let's see if we're close. We are really close. So a norm.dist function then, when these conditions are met here, then you'll end up with answers that are really close. Okay. Now, one thing just to note here about the norm.dist function is that we could actually change this slightly here and so that we're not having to pull out our calculator. We could type in 100 times 0.3 right there. And instead of 4.583, you could actually put in that function square root of 100 times 0.3 times 1 minus 0.3. Or I guess you could put in a 0.7 there. And you should end up with, what do we got here? Oh, yeah, I forgot to put the second bracket for the square root here. That would be right in here. There we go. That's where the problem is. There it is. Okay. So you get the same answer there. And I'll just put that down like that. And just there. Now you can see the whole thing. All right, so that's how you use the norm.dist and norm.inverse functions to do all the problems in section N on the normal distribution. So that ends our lesson here. Thanks for watching.